Alright, this is the third and last video that I'm going to do on drawing Lewis structures for molecules and polyatomic ions. In this video, we'll go through two new ideas. The first being the axial and equatorial position, and the second being drawing 3D Lewis structures. So hitting more into scholarship level, as in like pointing into and out of the page, and in playing with the central atom. Alright, so let's first take a look at the question. It asks us to draw a three-dimensional structure for each of the possible isomers of the pentahalide PCl3F2. First, we have to decide the central atom. And the central atom in the molecule is typically the least electronegative element or atom. This way, it is better suited to share its valence electrons with multiple other atoms around it. So, in our case, the least electronegative species or atom will be our phosphorus, so P. So it will be our central atom. Right, now we have to go look at the first important idea of axial versus equatorial positions. If we're looking at a bird's eye view, like P over here, atom will represent by a circle. If we're looking from above, right down at a bird's eye view, we will find equatorial positions, which is technically like in the same plane as it. And then, I'm going to remove this. There will be one above and one below. Now, if we look in plane with you look something like this. This is the central atom. There will be one above and one below. And then there will be this. There will be one here, one here. Now, these four, 1, 2, 3, 4, represents these four that I've drawn. And then this one above and below are the two little circles that I've drawn stacked together. The one that goes around the central atom, as in like these four, are in the equatorial position, and these going up, that's above and below the central atom, are in their axial positions. So for any molecule, there are only two atoms can be in the axial position, one above and one below, and they can be either 3, 4, or even 5, 6 atoms occupying the equatorial positions, which is the atoms going around it. And in 3D Lewis structure drawing, we usually do this. Let's say we have P here, and let's say it's PF5. We don't care about the charge yet. We're just gonna draw the structure. It'll be one F at the top, one F at the bottom, and then there are three Fs left that we'll have to draw, and those three will occupy the equatorial positions. One will go in plane with the phosphorus atom, one will go into the page, and one will go out of the page. And this is our 3D Lewis structure drawing. This brings us to another important idea. If you see this dotted line, this means going into the page. And then if you see this wedge or this filled out triangle, it is going out of the page or towards you. So, so let's try draw this again. This goes out of the page. Doesn't matter which order you draw it in, but this goes out of the page. This goes into the page. And if you can just see that it's kind of like a 3D drawing, right? These three are occupying the equatorial positions that goes around the P atom, and these two that's above and below occupies the axial positions. Right, let's actually get into the question now. We have PCl3F2. As mentioned earlier, P is the least electronegative atom, so it will be the central atom. And then Now it's asking for all the possible isomers. Isomers being like same number, like same structure, different bonding. So how could F and the three chlorines, two Fs and three chlorines, be arranged differently around P to have different isomers? First, we can say both the Fs occupy the axial position, and the three chlorines occupies the equatorial positions. That's one way. Second way is only one F occupies the axial position, and the rest will go around around P at the equatorial position. The last possible isomer will be none of the chlorine or fluorine atoms occupy the axial position, and the rest that hasn't been said goes around it. So there are only three possible isomers, although there are like 5 different bonds around P, because we know the axial position and equatorial positions are different things at different places, and you can't really mix them up. So we can say there are 3 possible isomers, because you can either have both Fs occupying both axial positions, one F occupying one axial position, or no fluorines occupying the 2 axial positions. Right, so this is how we do it. And for this shape, which is a trigonal biplanar, the bond angles between the atoms at equatorial positions are 120 degrees, and the bond angle between atoms on the axial position are 90 degrees, so right angle. Now if we look at the second part, the Vesper theory assumes that the bond from the central atom to an atom at lower electronegativity occupies more space than the bond from the central atom to an atom of higher electronegativity. What it's saying is that the atom with lower electronegativity will occupy more space, or will want more space. In this case, fluorine is the most electronegative, is the atom with high electronegativity, so it occupies less space than chlorine. And it asks which isomer is most likely to occur. I'm not gonna comment on polarity for this video, because that's not our aim. So which is most likely to occur? The isomer that is most likely to occur is the isomer that has the highest stability, and it is said that chlorine will occupy more space than fluorine, because chlorine has lower electronegativity, right? So you occupy more space. If both chlorines occupies the axial positions, then its bond angle is only 90 degrees. Versus if it's at the equatorial positions, its bond angle is 120 degrees. Obviously, when chlorine occupies the equatorial positions, you'll have more space, since it is 120 degrees apart from other atoms. Unlike axial positions, it will be 90 degrees. So the isomer that is most likely to occur will be when all the chlorine atoms are occupying equatorial positions, which is this structure, when the 2F atoms occupies the axial position. So hence this is the isomer that is most likely to occur. And yep, that's it.